Hello, civil engineers. Welcome back to the lecture. So far we have understood about the commercial building. We understood about the industrial building. About the residential building. Now here onwards, I'll be taking some of the industrial structures, and we'll try to understand that. And then we'll go to the high-rise building, right? So before we start with the industrial building, let me actually, whenever you start to work on any big projects, no, you'll be getting a kind of a general notes. Of course, in the previous drawing also we were getting a general notes, but in that notes you will not get everything. Basic things like what is the grade of a concrete, what is the grade of a steel, what is the lap length, only those things, and what is the SPC of a soil. Only those things were mentioned in the general notes. But when you work for a high-rise building, when you work for a industrial projects, a lot of things will be mentioned. So that is called as a general notes. First, we'll try to see that. Now, coming to the industrial buildings are those buildings, let us say if we are putting up a warehouses and all, right? If you have seen the Flipkart warehouse, or if you have seen the Amazon warehouse, or maybe some big automobile industries where the manufacturing of the car, the scooters and all happens, they don't, they require a huge space, right? So those buildings, what we construct is called as a industrial buildings. Got it? Yeah. So now this is one of general notes what I have for this particular building. So we'll take up this particular thing and we'll try to understand. So first here a lot of notes is given. This is especially for the steel structure. Right now we are not discussing on the steel structure. When I take up the PB drawings, there I'll take care of this. Now we'll see only the concrete point of view. So first again, general notes. Coordinate this drawing with relevant architecture and service drawing. That means whatever architectural drawings you'll get, you need to correlate this drawing with that. And service drawing in the sense like MEP, mechanical engineering, mechanical, electrical, and plumbing will be having a separate drawings and a separate department. So with that, you need to correlate your structural drawing. Do not scale, only written dimensions are to be followed. All dimensions are in mm. So again, when you're working for a small 30 by 40, when you had seen that G+3 residential building and all, no, there usually they mention in terms of feet and inches. But when you work for the big companies and when you work for a bigger project, so there everything will be in terms of mm. Got it? Now, notations, abbreviations, and symbols. So this you need to understand. Figures with, that means wherever you find a figure which has a symbol like this in the plan, that indicates it is a slab thickness. Okay. So wherever you, in the future drawings, I'll be showing you. For example, I have one drawing here, but here that slab thickness is not mentioned. Anyhow, not required. This is for the foundation details. Here also that is not mentioned, not an issue. Try to understand the concept, that is enough. So wherever you find a figure something like this in the plan, it means that here inside this they are going to mention what is the slab thickness. And wherever the figures at the right of the symbol in plan, elevation in mm. That means wherever you find a symbol something like this in a plan, then it means it is telling about the elevation. Okay, that what height is your building, especially in terms of the plan. If you're looking at your drawing in the section part, and if you find a symbol like this, it means it indicates that it is an elevation. Got it? That means if, for example, I've seen a drawing, I'm looking a plan, and there they have mentioned this drawing. That means this speaks about the elevation, whether it is at 1 meter height, 2 meter height, or 3 meter height. If I'm looking at a drawing that is a section drawing, and if you find a symbol something like this, even that means also it's an elevation. Got it? Now note down these things. NTS stand for note to scale. EGL stand for existing ground level. So in the drawing again, they'll not mention existing ground. They will just write EGL. So it's understood that it's called as existing ground level. FGL is called as finished ground level. Next is PL is plinth level. STP stand for stirrup. NGL stand for natural ground level. Got it? So these are the things which you need to understand. Now you can even note it down so that whenever you go for the interview, there is a chance they may ask you what is the full form of EGL, what is NTS in a drawing, what is NGL in a drawing, what is PL in the drawing. So all these things you should be knowing. Yes. Next, coming to the rebar, that is reinforcing steel. Unless otherwise specified, all reinforcement shall be of high yield strength deform bar. That means whatever reinforcement you are using, it should be HYSD bar. Okay. So this indicates that HYSD bar. Let me write it here. So HYSD bar. Okay. Of course, nowadays we have TMT bars also, but here it is mentioned you need to use HYSD bar. So again, it's telling that conforming to IS 1786 with minimum yield strength of 415 Newton per mm square. That means if you want to understand more about the bar, like what is the carbon content and all, then you can refer to IS 1786 code book. There everything will be mentioned regarding the rebar and the minimum yield strength. That means the minimum rebar that you're supposed to use in this particular construction should be 415. But nowadays we don't have 415 available. So you can go with the 500 Newton per mm square steel. Got it? All reinforcement steel shall be of tested quality. That means whenever you bring all this rebar to the construction side, will not directly use it for the construction. So I told you there will be an engineer by name quality control engineer. So once the entire lorry or a ton of that steel comes to your site, you'll be taking it to the testing lab where we'll do the testing of that particular rebar. Suppose if I had brought Fe 500, I'll do a testing on that whether that particular rebar is having a yield strength of 500 Newton per mm square or not. I'll also check what is the carbon content present in that. I'll check what is the elongation percentage in that. I'll I'll do the test. I'll do the bend and rebend test. That means I'll try to bend that rebar and I'll try to rebend it. So let me check if there is any cracks forming in that or not. So there are many tests which we need to conduct. And once it passes all the tests, only then I'll use that particular rebar for the construction. So that is why it's telling steel shall be of a tested quality. Now come to the concrete. Unless noted otherwise, concrete mix shall be of M25 for all elements and conforming to IS 456-2000. That means whatever concrete you are using in this particular structure, it should be made up of M25 grade of concrete for all elements. All elements in the sense beam, footing, column, beam, slab, staircase, whatever RCC element you are putting up, it should be M25. Got it? And in order to know more about the concrete, okay, in that case, you can refer IS 456-2000 code book. Got it? Now come to the cover part. Unless otherwise specified in the drawing, DRG stand for drawing. Clear cover to the main reinforcement shall be as follows. For the beam, it is usually 25 mm. For the slab, we keep 20 mm. For the footing, it is 50 mm. For the column, it is 40. For the retaining wall, it is 25. For the water tank, it is 25. Anyhow, in this particular project, we'll be speaking only for beam, footing, column, and retaining wall. Okay, we'll not be having any water tank here. Just in case if you have a water tank or a sump tank, in that case, you can go with the 25 mm. Got it? So all these things you should note down and you should remember because these are the questions which they will ask you in the interview. Next, the safe bearing capacity of a soil for the design of raft has been taken to be GL -1 to 6. That means GL means if you are standing in the ground level, from the ground level up to 1 meter, from 1 meter to 6 meter, you are getting a soil bearing capacity of 9 tons per square meter. From GL -1 to 6, you are getting 13 tons square per meter at 2.5 meter depth. In case of doubt regarding the soil bearing capacity, during excavation, the matter shall be reported to the consultant. So here what they have given, they are telling that this much at the depth of 2.5 meter, you are getting all this bearing capacity of the soil. If you don't get such bearing capacity at the soil, those things can be brought to the notice of the consultant. Now, coming to the construction details. Okay, unless otherwise specified, minimum lap length shall be development length of the larger bar lapped at any section. What do you mean by this? That means wherever what is written, minimum lap length. Minimum lap length shall be development length of the larger bar lapped at any section. Okay. So see, I told you about the lapping. Whenever you're lapping two bar, it's called as a lap length. Got it? So it's telling us whenever you're doing the lapping at any section, it shall be the development length of the larger bar. What is development length? So again, development length, there is a separate table that is given. But usually development length, what we can do is we can take 50 times the diameter of the bar. Usually we can take that. But if it is mentioned in the drawing, then we have to take the same diameter of the bar. So it's telling us you can take 50 times the diameter of the bar. Then it's adding one more word of the larger bar. Suppose if you are doing if you have two bar, this is bar number 1 and this is my bar number 2. This is 16 diameter bar and this is 12 diameter bar. So out of 16 and 12, which is larger? 16. Then I'll take care of 16 here. So 15 to 16 is 800 mm. So 800 mm will be my lap length. Got it? So that is what they are trying to tell us, that where it is, shall be development length of the larger bar. Not more than 50% of the bar shall be lapped at any section. The location of bar shall be avoided. That means what is telling, I told you, whenever you are lapping the bar, you should not do the lapping of a bar for more than 50%. If you have 10 number of rebar, only 5 bar has to be lapped at one section. Remaining 5 bar, you lap it at the another section. So it's telling not more than 50%. Now, floor beam slab close to the mid-span bar and close to the support in the top bar shall be avoided. Okay, beam slab close to the mid-span bar and close to the support in top bar shall be avoided. Unless otherwise indicated in the drawing, construction joint should be approved by engineer in charge at the site. Okay, this should have been site. Okay, so what is the first point he is telling us? Floor beam slab close to the mid-span bar and close to the support in the top bar shall be avoided. So again, simple concept. Forget about all these things. Whenever you're doing the lapping of a bar, be it column, beam, slab, wherever the bending moment is minimum, we need to do the lapping of the bar. I'll repeat it again. Wherever the bending moment is minimum, we need to do the lapping of the bar. Or wherever is a point of contraflexion, there we are supposed to do the lapping. This is a concept. Okay. Now, in case of beam, what happens? So I'll draw it here. In case of beam, what happens? You have to note down all these things. I'll just quickly write here. In case of beam, if you're lapping the top bar, then I'll write where you should not lap it. Okay. Or I'll write where you should lap it. Okay. That will be simple. So in case of beam, if you're lapping the bar at the top, you should lap at the center or beyond L/4. Finish. That is for the top bar. Now coming to the bottom bar, for the bottom, you should lap near support or within L/4 Now understand the concept. Why this thing we need to follow in the beam? For usually if I take a beam, if this is my beam, I'll put a fixed support here. Okay. And this is my beam. Got it? So usually what is the behavior of your slab, of your beam? Usually we'll be having a negative bending moment here. Then it will turn into a positive bending moment. Then it will be a negative bending moment. So this will be negative. This will be positive. This will be negative. Okay. And now I'll draw one more line here and I'll say that this particular line I'll draw. This is my top bar. I'll say whatever we are getting above this, it is my top bar. Whatever I'm getting in the bottom, it is my bottom bar. So top, middle or beyond L/4. That means for whatever bar you are going to lap at the top, you should lap here at the center. Why? Because you have a negative bending moment near the support and you have the negative bending moment near the support. So I told you lapping should be done wherever the bending moment is minimum. Now in this particular thing, tell me where is bending moment minimum? Of course, here you cannot lap. Here that means here in the sense this much portion you cannot lap because up to this portion your bending moment is maximum, right? You can see it's on a higher side. But this is a point which is called as point of contraflexion where your bending moment changes its sign. Similarly, from here to here, your bending moment is maximum. Up to here, we have bending moment maximum. It's maximum here. By the time you reach here, it will be minimum. But this is a point where the point of contraflexion happens. That means from beyond this point up to here, this is a middle portion, what I say. So here I can do the lapping. For which bar? Only the top bar. Only for the top bar. Got it? Now, come to the bottom. So bottom is telling near the support. That means for the bottom, what has happened now? This is bottom. The bottom, this is your maximum bending moment. This much portion, your bending moment is maximum. Up to here, this much portion. So that means I cannot do any lapping in this portion because my bending moment is maximum. But beyond this point, is there any bending moment? No. I mean, there is a bending moment, but it's not a maximum bending moment. Maximum bending moment was here at the center. After that, it went on decreasing. It reached a point of contraflexion. And from here, it was a negative bending moment. But right now, I'm speaking in terms of bottom reinforcement. For the bottom beyond this point, there is no there's no bending moment. The bending moment is very minimum. So wherever the bending moment is minimum, we'll do the lapping. So it's telling near the support. So this is support number 1. This is support number 2. So in this distance, I can do the lapping of my bottom bar. Understood the concept? In this portion, I can do the lapping of my bottom bar. Now, to make it in a better way, what people have found, what the code book says that you do it the middle. But exactly middle means it can be here also. 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 It can be here. That is up to you. You need to decide whether you want exactly at the middle or you want it somewhere here. But it should go beyond L by 4. L by 4 means this much distance, whatever we have, no? This much we consider this much distance as L by 4. If my span is 10 meter, L by 4 will come out to be 2 point. So this is 2.5 meter. Okay. And this is also 2.5. So beyond 2.5 meter from both the support, you do the lapping. Suppose if it is a 10 meter, so 2.5 is gone here, 2.5 is gone here. So 2.5, 2.5 is 5 meter. That means the middle portion, whatever I have, whatever is left, that is only 5 meter. Now in this 5 meter, you lap anywhere. If this is 2.5 meter, it may be 3.5, it may be 4.5 here, it may be, let us say 6.5, or it may be 7.5. In this distance, wherever you want, you can do the lapping. Understood the concept? Now for the bottom also, you are telling you do at the middle portion, fine. But middle, beyond middle, I can do. That means I can do the lapping here also. I can do the lapping here. I can do the lapping here. I can do the lapping here, 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 here. So it's telling within L by 4. So this is L by 4 portion within. So in the bottom, it is within. Within this much portion, you have to do. Beyond this, it will be a maximum bending moment. I cannot lap. So within this L by 4 you do. Within this L by 4 you do the lapping. Understood the concept? Got it? So just try to remember this. Okay. Now you will tell me, sir, why it is L by 4 only? Why it is not L by 5? Now it has been found through practice and after doing lot of research and lot of, analysis and all. Usually this bending moment, shall I delete everything? Okay, I'll delete everything. So usually, okay, that also went, no? Okay. Usually it has been found if I take any beam, any beam in the sense a fixed beam, and if I try to plot the negative bending moment, positive and negative, it has been found this effect of negative bending moment, is predominant or it is dominant up to L by 4 or it is more effective up to L by 4. This is L by 4. This is L by 4. Beyond L by 4, your negative bending moment is very less and it will turn into a sagging bending moment. So through lot of beams, we have done the analysis and we have checked it. So that is why we say L by 4 is a standard value that you can take. Now, this may not be true with all the beams. This may not be true with all the for few beam it may be L by 5. For few beam it may be L by 3. But I cannot do, if I put a structure, let us say if there are 100 beams, do you think for all 100 beams I'll keep on doing like, okay, for this beam number 1, you do up to L by 3. For beam number 2, okay, you do up to L by 5. For beam number 3, you do up to L by 3. So it's practically not possible. So we have standardized a value. We say that is fine. For all the beam, we'll take it as L by 4. Got the concept? But actually, if you look into the ETABS value, in the ETABS when I did the design analysis, if you have seen that properly, for each beam, it will give you what is your point of contraflexion, what is the point of contraflexion. But for each beam, we cannot sit and pick where is that point of contraflexion, that we cannot do. So what we do, we standardize it and we say L by 4. Simple concept. Understood? It's very simple. Just you have to practice it. So this was about the beam. Same thing you have to do it for the this thing also, column. For column, I'll explain it here. For the slab also, it's the same thing. Yeah. Now, the foundation that is lean concrete in 1:4:8 mix shall have a coarse aggregate of size not more than 40 mm nominal size. That means wherever you're putting this PCC, that is called as plain cement concrete. So plain cement concrete is also called as a lean concrete. Why it is called lean concrete? Because in PCC, usually your aggregate size will be up to 40 mm. For RCC construction, like for footing, column, beam, slab, staircase, my maximum size of aggregate is 20 mm. I never put an aggregate size more than 20 mm in the foundation, in the column, beam, slab, and staircase. But in case of PCC, I can use the aggregate more than 20 mm, usually up to 40 mm, we try to use it. So since the aggregate size is more, what will happen? Your concrete, your cement, more amount of cement will go inside the aggregate, because since the aggregate size is bigger, the voids is also bigger. If the voids are bigger, large amount of cement paste will be entered into the void. As a result of that, there won't be a good lubrication between the aggregate. As a result of that, what will happen is we'll get a harsh concrete. So this harsh concrete is sometimes called as lean concrete. That means the cement particles which is there in the concrete will be very less compared to the concrete that we put in the footing, column, beam, slab, and staircase. So it's called as lean concrete. So there you go with the 40 mm aggregate size. That is fine. Why? Because it will not take any load. Only to give a uniform surface, we provide a PCC. And since you have to give a uniform surface, you go with a higher diameter of the higher size of the aggregate, so that you are saving on the cement cost there. Okay, because ultimately that will never take a load. It is only put up to take care of the what you call uniform surface. I want a uniform surface, so I put a PCC. Got it? Yeah. So what is the ratio you're supposed to use? 1:4:8. So 1:4:8 is actually M 7.5 grade of concrete. So 1 part of cement, 4 part of sand, and 8 part of coarse aggregate. You are supposed to use it. And this grade is called as M 7.5. Sometimes people use a ratio of 1:3. Let me write it properly. Yeah. Sometimes people use a ratio of 1:3:6. So this grade is called as M10 grade of concrete. So you can even use M10 grade of concrete for the PCC. So another name for PCC is called as lean concrete. Got it? Fine. Simple. All brickwork shall be 1:5. Wherever you're doing a brickwork, okay, you use a mortar in between the brickwork, right? So that ratio should be 1:5, where 1 part is cement, and this should have been 5. By mistake, he has written 6 here. This should have been 5. Okay. Yeah. So all brickwork shall be 1:5. That is 1 part of cement, 5 part of coarse sand, mortar of 230 thick wall, and 1:4 mortar in 115 thick wall. That means you put up the brickwork, right? So usually if it is a outer brickwork, we go with a 9 inch. If it is a partition brickwork, like if you have a toilet, okay, not toilet, let us say you have a bathroom where one part you are using it for, one is bath, the other is for the toilet area. So you put a wall, right? That is called as partition wall. There you can use 115 thick wall, that is 4.5 inch wall. But outer wall, from security point of view and all, usually the outer wall of your house will be 9 inch thick, which is 230 So wherever you are using a 230 thick wall, you need to use a cement mortar of 1:5. And wherever you are using a 115 thick wall, you're supposed to use a cement mortar of 1:4. Why is that so? Because 1:4 is richer mix compared to 1:5. So understand this concept. Again, they'll ask you in the interview, if you go, if you're applying for the job of a site engineer, they'll ask you, like, if it is outer brickwork, what is the thickness you're supposed to keep? If it is inner, how much you're going to keep? What is the cement mortar that you're supposed to use? So if it is 1:4 ratio, we go. If it is 115 thick wall, we go with 1:4. And always remember, 1:4 is a rich mix. Is a rich mix compared to 1:5. Okay. In comparison to 1:5, 1:4 is richer mix, because here only 1 part of cement and 1/4 part of aggregate. But here 1 part of cement and 5.5 part of this thing, not coarse aggregate. This one sand. Okay. And this is also sand. So here the sand amount is more, the volume will be more. As a result of that, the strength will come down compared to 1:4. So for 200 thick, already your wall is thick. Again, you don't require too much of strength. So that is why what we do, we go with 1:5. But 115 thick wall is, I mean, the size is very small. So it will have a lot of vibration, and also the strength will not be more. So in order to increase the strength, we'll go with a rich mortar, that is 1:4. So if I take 1:4 mortar, so the cement mortar will have a good strength. As a result of that, your brickwork strength will also be good. Keeping that in mind, we go with 1:5 for outer and 1:4 for the 4.5 inch thick, which is 115 wall. Got the concept? Yeah. After that, okay. Brick masonry wall shall consist of square units built to horizontal courses with broken vertical joints in accordance with IS 2212. The mortar used for masonry shall be conform with requirement of IS 2212. The minimum crushing strength of brick shall be as specified unless noted. Brick joint shall be of fully mortar bed with frog, if any, uppermost, so that cross joints are completely filled with mortar. The this is not required. I mean, not required in the sense, again, these things is more from execution point of view. Most of the things I've covered in my site engineer course. There you can go through that, because it will, I cannot just explain you here. I need to show you a lot of videos and images, and only then I can teach you this in a more better way. So most of the things, whatever is mentioned, it is explained in my site engineer course. You can watch, you can, listen from there. Okay. So last point is, all brickwork shall be 1:5. That is 230 thick wall, and 1:4 mortar in 115 thick wall. That is already mentioned here. Then other than that, That's it. It's the same. These 2 points are repetition of the previous point, and these 3 points are more from the way you are supposed to do the brickwork. So it's not much needed from structural point of view. Got it? So I think all the things what is mentioned in the general notes I have covered it. So now we'll start with this particular thing. Okay. So one by one, let me start. First, what I'll do is I'll start with this. Okay. So this is already we have understood, but here he has given it in the form of a table. So what he's trying to tell us is telling us if you're putting up a stirrup, if this is your stirrup, then he's telling us, I told you already, you know that also, this hook, whatever you are providing, okay, this hook, whatever you are providing, it has to be minimum how much? This is 45 degree. This angle from through which you are bending, it should be 45 degree. And this length, hook length, I told you minimum it has to be 75 mm or 10 times the diameter of the bar, whichever is higher. Here is telling 10 times the diameter of the bar, mi and for minimum or greater or equal to 80 mm. Here instead of 75 mm, he has taken 80 mm. Maybe from the code book he has taken it. But usually, it was actually 75 mm. Maybe now it has they have made it to 80 mm. Not an issue. Okay, not an issue. So because 5 mm doesn't make any difference. So this hook length you're supposed to keep minimum 75 mm or 10 times the diameter of the bar, whichever is higher. Got it? Which you already know. But you need to remember all these things because in the interview they will ask you all these questions. Fine. Next, what is telling us? This is again same thing. Same thing. Say this is for 45-degree hook. Okay. Sometimes you will provide a hook like this also, no? Like this cross tie in the stirrup we were providing. In the column we were providing something like this. You remember, right? Single tie. So then also you need to do the same thing. This will be 10 times the diameter of the bar or 80 mm. This also will be 10 times the diameter of the bar or the 80 mm. It's up to you. I mean, you need to follow this. Okay. So it's written typical. TYP stands for typical beam stirrup or column tie. One and the same. After that, where shall I go? Huh. Let me speak something on the development length. Now here you see development length for the deform bar, development length for the deform bar. If you're using a 415 Newton per mm square rebar, then you need to follow this table. If you're using a rebar of 500 grade, then you need to follow this. Anyhow, right now we don't have 415 available in the market. We'll not look into this. Only concentrate on this particular part. So now he's telling us if you're using a diameter of 8, 10, 12, 16, 18, 18 is not available, but still they have written 18, 20, 22, 25, 28, 32, 36. And if a grade of concrete is M20 grade, then if you're putting up a 12 diameter bar, you need to give a development length of 680. Got it? Suppose if it is a tension bar. Suppose if it is a compression bar, for a 12 diameter bar, for M20, you need to provide 544. So again, what is this compression and tension bar? So for that, you need to understand the beam. For example, if I take a beam, I'll draw it here only. And if it is and this is a neutral axis, what we have. So this is neutral axis. So if it is a fixed beam, usually what happens is, this much part will be in tension, this part will be in tension, this part also will be in tension, and this part also will be in tension. And all other part, that is this part, and this part will be in compression. Got it? So this is one way. Otherwise, if I take a normal simply supported beam, or if I take a simply supported beam, this is how it is, simply supported beam. This is a positive bending moment. If I put that in terms of a beam, so usually this will be my neutral axis. This is neutral axis. So the below portion will be in tension and the above portion will be compression. So wherever you have compression, there you will be putting up a compression bar. So in that case, you need to give a development length. If you're taking a 12 diameter bar for M20 grade, it should be 544 development length. And if it is a tension bar, then you're supposed to give 680. But again, practically, it's little difficult for you to keep all these things on the side. That for compression, you keep it separately. For tension, you keep it separately. So practically, from execution point of view, will not be so much accurate. So what we usually do is, whatever is provided in the tension, no, the same thing will provide it in the compression also. Of course, according to the calculation, it will come like this. But keeping execution point of view, because on the site, it's not a single beam. You'll be having 50, 100, 200 beams. So every time you cannot go take a tape and do the exact measurement and do all those stuff. It's not practically possible. But what we can do is, whatever is there in the tension, no? So tension bar, whatever we have, it is 680 compared to your compression. So what we do is, we usually provide whatever length is given in the tension, no? That only we try to provide on the site. So this is depending on the grade of the concrete. Okay. If you have M20, this is the value you're supposed to take. If it is M25, you're supposed to take this value. If it is M30, you're supposed to take this value. Now the big question is that how these things are coming. So for that, you need to refer IS 456 code book. So this is IS 456 code book. And if you go to page number 42, and if you go to clause number 26.2.1, it's written development length of bar. So this is the formula what we have. So always remember the formula, and that is enough. So LD stands for development length. This is diameter of the bar. Sigma S is the stress in the bar at the section considered at the design load, and tau BD is the design bond stress. So in this diameter is unknown. Of course, you can put 8, 10, 12, you'll get answer. The sigma x is stress. So stress at the bar is usually 0.87 into Fy. It's not mentioned, but you should know. The stress in the rebar is 0.87 into Fy. Suppose if I'm using a 500 grade of steel, so you multiply this. Tell me what is the answer you're getting. So what you should do, 0.87 into Fy. So 0.87 into Fy. Fy is 500. So I'm getting 435. So I'm getting 435. Okay, this is 435. Divide by 4 times the tau BD. 4 is constant. What is tau BD? Tau BD is design bond stress. So where it is given? So they have mentioned it. The design bond stress is given in 26.2.1.1. That is this part. See? So here they are telling us if you're using a M20 grade of concrete, you need to take tau BD as 1.2. If you're using a M25 grade of concrete, take it as 1.4. If you're using a M30 grade of concrete, you have to take 1.5, and so on. For deform bar, according to IS 1786, this value shall be increased by 60%. So usually whatever bar we are using, they all are like HYSD bar, deform bar. In that case, this value, whatever we have, no, it has to be increased by 60%. You need to multiply this value by 1.60. Got it? That is 1.2. So 1.2 into 1.6 we are supposed to do it. So all this calculation will be done by the structural engineer. You don't have to do anything on the site. But sometimes if it is not given, how the site engineer will do? Site engineer will directly take a formula, take 50 times the diameter of the bar. Simple. You are on the safer side. Whatever is the diameter of the bar, you provide it, be it in compression or tension. Okay. So the same calculation we can try to do. Let me go for M20. I'll do for M20. For M20, it is 1.2. Okay. Remember the value 1.2. So we'll do the calculation. So development length, LD will be diameter. So diameter, let me keep diameter as a constant only. I'll write diameter, dia, multiply by sigma s. Sigma s is 0.87 into Fy. I'll go with 500 bar and divide by 4 times into what is tau BD? Tau BD is for M20 grade, it is 1.2. So do this calculation, tell me what is the answer you are getting. Dia you keep as it is. Sigma stress is 0.87 into Fy. I'm taking 500 rebar. Divide by 4 times the 1.2. So I'm getting 90.625. How come it is 90.625? And it is wrong, no? 90.625 cannot happen. Sigma stress is 0.87 into Fy. One thing can happen. Then maybe somewhere I'm doing it wrong. Let me do one thing. Give me a minute. Let me check. I have a manual calculation with me. Give me a minute. Yeah. So I got the answer for that. Yeah. Actually, what we did, no, since we are taking the bar, it is our HYSD bar. Okay. So it's telling for deform bar, you have to increase this by 1.6%. So that means what we are supposed to do, this answer, you multiply it by 1.2. What you did, no? Wait. 1.2 into 1.6 will do. Why 1.6? Because we have to increase it by 60%. So that is why I'll multiply this by 1.6. Okay. Now you tell me what is the answer you are getting. So I'll do it again. 0.87 into Fy, 500 divided by 4 times 1.2 multiplied by 1.6. Yeah, I'm getting 56 point. No, wait. 0.87 into Fy divided by 4 into 1 point. Wait, I think we are doing one mistake, no? Is that it's 1.2. Huh, okay. We'll do that. We are doing for M20, no? Yeah, 1.2 into 1.6. So I'm getting a 54. What I'm getting? I'm getting How much you know? 54.68. I'll take 55. So 50 times 55 times the dia it is into dia. So this is a formula what I got for how much? For M20 grade. I can write if you want M20 grade. Similarly, tell me for a M25 grade of concrete, same thing. Again, dia multiply by 0.87 into 500 exactly, divide by 4 into what is tau BD? Your tau BD, it is 1.4 times into 1.6. I'll show you why it is 1.4. It is mentioned in the table. Do this calculation. Simply instead of 1.2, take 1.4 and you'll get 46.87. I'll take 47 times the dia. Got it? This is for M25. Now we'll try to verify this. See here. Now I took for M25, it is 1.4. Got it? Now for bars in compression, the value of bond stress for the bar in tension shall be increased. For bars in compression, the values of bond stress, okay, this is not required. Now we'll try to verify this. So it's 47 times the diameter of the bar if it is M25 grade. Now what is the table that we got here? Okay, for the table I'll confirm it now. Let me search for Fe500. This is Fe500 and I did it for a random. Okay, so let me go for one bar. I did it for M25. No, where is M25? This is M25. This is M25 portion. Now this is a formula what I have. Now if I input this diameter here, I'll get the answer. I should get the answer. Let me start with 12 diameter. For 12 diameter for M25 grade, I should get 583. So my formula is 47 times the diameter, right? Isn't it? Yeah. So 47 into 12 if I do, 564 I'm getting. So by 544 they are putting here. So 583 they are putting. How come? For M25, I should get, my answer is 49 times the diameter of the bar. And 47, no? Yeah, 47, M25. Let me go with this one. It is 55 into 12 diameter. See, what is happening, you know? For M20, I now let us say if I want to find for 12 diameter bar, for M20, I should get 680, my answer. So if I do like this, 55 into diameter, I'm going for 12, no? 55 into 12 is 660. This is 12. 660 mm. This is the answer I should get. Here they are getting 680. I don't know from where additional 20 mm they are getting. Same problem is happening here also. If it is a 12 diameter bar, I'm taking M25 grade of concrete. So what will be my formula? 47 times the diameter. So 47 into 12 you do. 47 into 12. So I'm getting 564. I'm getting 564. This is for this with this formula. But here the answer is 583. Roughly 20 mm excess they are getting. I don't know how they are getting roughly 20 mm excess. Because even this also is not matching, in that case. Not an issue, but you understand this is a concept. There is no nothing wrong what I have taught you. This is a concept. Maybe sometimes different structural engineers follow in a different way. Maybe he has taken another 20 mm extra or something like that. Even I'm not sure. But the way of doing is this one. Okay, this is a formula. You need to understand the concept. See, I have a book with me. All these things I have written it here. The same thing I'm getting here. Here, whatever I've done, same answer I'm teaching you. Okay. Let me try to check. No, whatever I thought is correct. Maybe sometimes no, they try to be on the higher side. Yeah, for development intention. Fine. Hmm. Fine. Now, what is happening? You understood one concept here. See, in some area we're getting 50. For if I'm taking M20 grade of concrete, I'm getting 55 times the diameter. If I'm taking a M25 grade of concrete, I'm getting 47 times the diameter of the bar. So that is the reason what we do. On the side, to be on the safer side, you say you take 50 times the diameter of the bar. Okay, to be on the safer side, and to make it easy, we go with 50 times the diameter of the bar in the site on the site. Okay, one thing you understand, as the grade of the concrete keeps on increasing, your development length is coming down. Did you see that? For M20 it is 55, for M25 it is 47. If I go for M30, no, it will even come down to around 41, I guess, 41, 42. So as the grade of concrete increases, your development length comes down. Why? Because your grade of concrete is directly depending on this particular formula. The more the grade, the more will be your strength. The more the strength, what will happen? The development length required will come down. Simple. That is actually the concept. because this development length is given so that it can transfer the stress from your rebar from the from your rebar to the concrete. We provide this particular development length. So more the grade, it will have more strength. If more strength is given through concrete only, then the development length requirement will be less. So you can see the same thing. So if you want, you can even do the formula for M30 grade also. I'll quickly do that. M30. M30, it is 1.5. Okay. Now quickly do that. I'll do it here only. So 0.87 into F5, 500, 85 into 500, divided by 4 into tau BD. So tau BD is 1.5. We'll increase it by 60% for tension bar. Yes, I'm getting 44.27. Got it? I'm increasing the grade of concrete. Now for this, it is coming how much? 44. For M30, it is 44. Simple. But again, you can see 55, 47, 44. So we'll try to say you provide 50 times the diameter of the bar on the side. Suppose if it is given in your drawing, then you can follow the same thing on the side. This thing. But you should know, as an engineer, you should know how these values are coming. Simple. So I hope up to here, your concepts are clear. I'll wind up this lecture here only. Of course, there are a lot of things to explain, especially the column part. We have a lot of things to explain. And I also told you that we'll be taking this particular drawing and we'll try to understand. So those things I'll cover it in the next lecture. So we'll see you back in the next lecture. Thank you.